Hello, everybody. My name is Michael Leamy, and I'm a professor of mechanical engineering at the Georgia Institute of Technology, or more commonly, Georgia Tech. So, I do research in acoustics, of course, and NewFoS, all about acoustics, but I also do research in nonlinear dynamics and vibrations. And I tend to merge these disciplines together doing the work that I do or the research I do for NewFoS. So, what does it mean by nonlinear? Well, um, when we say something is linear, we say that there's a linear relationship, let's say, in how something responds to stress or maybe forces. And we're saying, for example, if we stretch a rod, that the stress, which is the force divided by the area, so if we put a force on a rod, we're going to have some amount of stress in the rod, that the strain, which is a measure of how much it deforms, is linearly proportional to that force. And that's a classic linear relationship. And this is very well understood. And in fact, the equations that govern the response of the system for a linear system usually have known solutions, unique solutions, things that we as engineers are very comfortable with. Now, on the other hand, if this relationship becomes nonlinear, suppose we stretch a rod, we put a known amount of force, and we get one displacement, but then we double the force, and we find that we don't have double the displacement. Maybe we have a little less, we call that a hardening system, or perhaps we have a little more, which is a softening system. A classic example would be a rubber band. You may have taken a rubber band and it becomes more difficult to stretch it. The more we stretch it, of course, that's the linear behavior. But then we come to a point where essentially we can't stretch it any further. It's as if we added almost an infinite amount of force and we can no longer stretch the rubber band. Well, that's a hardening behavior. That's really stretching of polymer chains that are leading to this hardening behavior, and that's very nonlinear. Now, when that occurs in a system, particularly a system that's dynamically excited, then we have the potential to have higher frequencies generated or even lower frequencies, particularly in softening systems. And this makes our ability to analyze these systems very difficult. Now, not only are the systems difficult to analyze, they may in fact have multiple solutions, just like you're familiar with the quadratic equation. That really is the very simple algebraic setting where you might encounter for the first time a nonlinearity. And we know that in the quadratic formula, for example, negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Something that many of you have memorized in high school perhaps and later. Well, we know that there's two solutions there because of the plus minus. And in fact, we can have an equation, a quadratic equation with real quantities, right? Not complex as in the imaginary number I having a real and imaginary part, but we can have these real equations, and even these equations may arise from some physical system we're looking at. And if it's quadratic, we're likely to get a complex solution. In fact, we get complex conjugate solutions for the quadratic equation. And that's just an example of what happens in nonlinear systems. We may get multiple solutions. In dynamical systems in particular, we may find some of those are stable and unstable. Stable meaning that they would physically arise. Unstable meaning if we could be at that solution, but if we had a very small perturbation to the system, that the solution would disappear. We would move away from the physical system. Okay, so that's really what I study. I look at acoustics, dynamics, vibrations, and oftentimes I'm looking at nonlinear systems in my research. Well, I'm now joining you from what may be the world's most cluttered lab, which is a lab I share here at Georgia Tech with another faculty member. That's what you can see behind me right about here is a laser Doppler vibrometer, which maybe I'll talk about as I continue to film. This is a little electrodynamic shaker, which is how we apply impulses to systems. We measure the responsive systems, including acoustic systems under the work for NewFoS, using this laser Doppler vibrometer. This is a very simple LDV, laser Doppler vibrometer, single scanning point, but we have very sophisticated LDVs that will scan a system relatively quickly and at very high frequencies, up to many hundreds of kilohertz. So what I thought I would answer next is, maybe what has been some impact of the work that I've done in these areas that I work in, and I'll go all the way back to my PhD, and then I'll bring you a little bit up to modern times. But my PhD was granted in 1998 from the University of Michigan, and there I was looking at drive friction as a nonlinearity in what are termed front end accessory drives and the vibrations and, in fact, the sound that originates from these systems. So, a front end accessory drive, or a FIAD, is the lingo in the industry. This is essentially the belt drive. So, in a vehicle, your engine is powering lots of other systems other than just the propulsion system, the system that's providing the propulsive effort to accelerate the vehicle. The engine is providing a pump for cooling, an alternator for generating electricity, which then recharges the battery. So each time you start the vehicle, you use some of that battery energy. There's energy, of course, all the time, electrical energy to power the HVAC, the heating, ventilation, air conditioning, the infotainment, etc. So many of these components are actually powered by the engine through a belt system, a serpentine belt, which is then spinning pulleys and spinning these various components. And back in the early and mid to late 1990s, the number one warranty claim, in fact, for vehicles were claims arising from the noises that this front end accessory drive made. And what was happening is that in the industry, vehicles were becoming more and more quiet, right? There was intense competition to make what consumers felt were quiet, quality vehicles. And as they did this, noises that otherwise would have been masked, and this is a very relevant topic today with electric vehicles, and I'll get back to that in a moment. But noises that were previously masked by other noise, like engine noise, etc., were being eliminated, and so new noises were arising. And one of the new noises were these noises from these front-end accessory drives. Now, why was this an important problem besides the fact that it was a source of warranty claims, and my PhD was funded by Ford to answer this question? It's because it was a very difficult question. We have this actually translating. So along its axis, we have this continuum, which is the belt that's translating. And it's in frictional contact with pulleys. In fact, that's how it translates power from the engine to these components I mentioned, is through frictional contact. And that frictional contact is nonlinear. Nonlinear because there's not a proportional relationship between, let's say, the torque and the sliding. Sometimes it slides and sometimes it doesn't. That's called a discontinuous nonlinearity. And this presents enormous challenges in trying to model and understand and predict the noise that ultimately comes from these systems. So in my PhD, I wrote a lot of software and solved these problems. And as I said, they were relatively complex problems. And to this day, that's actually software that's used at Ford Motor Company to predict the performance of these front-end accessory drives. Now, I'll skip ahead a little bit. I've continued to do acoustics work in the automotive space. So my students and I here at Georgia Tech in the last 10 years, we've developed isolation techniques for isolating the vibration from an engine that's then felt through the chassis. The transfer path is through the chassis or the unibody of the vehicle and felt into the passenger cabin. And as I said, this is work we've developed and patented. We have a patent for. And so the modern motivation and the modern technology that led to this work is really start-stop systems in vehicles. So you may have a vehicle, in fact, that will stop at a light. When you put your foot on the brake and come to a complete stop, the engine will stop. Literally no combustion will occur. And then as soon as you take your foot off, very rapidly, typically with a higher voltage system than had been traditionally on vehicles, which turned a 48-volt system, will spin a relatively powerful motor to get that engine up to speed as soon as your foot starts to move off the brake pedal, before you even have a chance to hit the gas pedal or the accelerator pedal more formally. The engine will kick back on. Now, this is a great system because, one, it saves fuel, right? Your engine's not running while you're sitting at stoplights and things. Also, pedestrians tend to be near stoplights, in at least in cities, urban areas, and so this saves emissions too. It saves people from really ingesting a lot of harmful, toxic emissions. All right, but the problem is many people defeat this system, right? They don't like this feel. They don't like the feel of the engine shutting down. They don't like the feel of the engine restarting. And so they may completely defeat or eliminate this system by turning it off and turning it off forever. And then, of course, the benefits are not gained. So we've done recent work on how we input shape that starter motor so that we're effectively canceling out vibration. And this would be maybe something in active acoustics, even though it's a vibrations, but you might call this an active acoustics technique. And then we've shown experimentally that, in fact, we can make it very transparent to the driver that their engine's ever being turned off or shut off. Maybe transparent's not the right word. We can, in fact, hide that so that they don't feel that. And then, of course, the hope is that they will not defeat the system. And maybe third, I'll just mention a last example of work that we've been doing here under NewFoS, and that's looking at multiplexing and demultiplexing acoustic channels using these topological insulators that I'm sure you've heard much about. All right, and so in our mind, a topological insulator provides these states, these interface states, that to us look like really circuit elements, and to us, I mean to my research group. So these are waves that do not geometrically disperse. So as I talk, of course, the further away that you are from me, the further the wave front, this spherical wave front, has spread out and the intensity has gone down. Well, in these interface states that we're able to make using topological acoustics under NewFoS, we can treat these much like circuit elements. And in fact, what my research group has done is devised reconfigurable topological insulators. So we take a 2D material like a plate that has unit cells that repeat, and we use active PZT elements to break asymmetry. Fundamentally, this is how we often realize topological states. But the point is, we have this plate and it's monolithic, okay? It's the same everywhere. It has these unit cells. But all we're doing is either turning on or turning off a circuit attached to a piezoelectric element. And a piezoelectric element converts strain to voltage and vice versa, okay? And so we can break symmetry, and when we break symmetry, we can introduce really topologically distinct materials, A and B, separated by an interface wherever we like in that plate. And so this allows us, for example, to first channel information through a topological state. Perhaps it's going straight across the plate. So we can start with an input A and go all the way to an output B. But we also may change the direction and come back this way, so we can reconfigure the plate and come back to an output C from A. So we have an input A, and then we have output B and output C, and we can just periodically switch from B to C, C to B, etc. And that allows us to take two channels of information from A and demultiplex them. First, then send them to B, and then later send them to C. And this is work that we've also patented. The hope is that someday that work may find its way into, for example, a communication device, a radio, maybe a military radio, maybe a consumer radio. And so that's some of the work that we do that has, societal and technological impact. Well, next maybe I'll talk a little bit about upcoming projects that we're doing as part of NewFoS. So I've explained a little bit about this multiplexing and demultiplexing. Multiplexing is really the inverse operation of demultiplexing that I described in some detail. Well, what we're doing under NewFoS is continuing that work, what we call RF applications of topological acoustics, radio frequency applications. We've introduced ways of creating an oscillator from a topologically protected defect, and we're exploring that experimentally presently. The idea being that we have, again, this monolithic system that's composed of repeated unit cells. And somewhere in there, using, again, a piezoelectric, a PZT element, we're able to tune away from the natural behavior of the material and introduce a little bit of a defect that's integrated into the lattice. And now there's quite a lot of mathematics behind why this is topological, but essentially what happens is by tuning, we take one of the natural frequencies of the system and we move it in from what's termed a pass band to a stop band, and we can in fact traverse that entire length of that stop band in frequency by tuning this piezoelectric element. And it's the presence of the defect in the band gap that's protecting it, because the energy that's stored in the defect has very little ability to leave because it's sitting in what's termed a frequency stop band. It can't propagate at those frequencies. And this can be used as an acoustic element that can give us a memory element, effectively, a 0 or 1. When the topological defect is present, we can think of that as a memory of holding a single bit at 1, or when the topological defect is not present, we can consider that as 0. Now that's a memory element that's using acoustics. We're also starting to explore how we take well, let me back up, I apologize. So we're also looking at acoustic transisting. So using this same platform, which is again a reconfigurable topological insulator, something developed under NewFoS, we can introduce interface states as I like wherever we wish. We could have material A, B, but we could also have material A, B, A. So we can have two topologically distinct materials, A and B, separated wherever we like out of this single monolithic material, because again, we're going to either turn on or off some shunts to these periodically placed PZT elements. Now, what we've been able to do is acoustic transisting, really electroacoustic transisting because of the presence of the PZT elements. But the idea is that we can use one source of acoustic energy along one interface state to enable another interface state somewhere else, which will then allow a second channel of acoustic information. So that is a transistor, if you like. We're using one source of acoustic energy to switch on or off another source of acoustic energy. And here you can see why we need to have ABA. We need to have AB, and that gives us our first topological state. And then we need to go back to A from B to A, and that gives us the potential to have a second interface state. And if you recall what I said, we treat these interface states really as circuit elements in my research. We don't have geometric spreading, we have the localized state. It acts much like a circuit element, but instead of transmitting electrons, we're transmitting acoustic energy. All right, but once you have a transistor, in fact, then you can build all the logic gates that compose a computer. That is the very basic building block. It can lead to OR, AND logic, something called NOT AND or NAND. And in fact, if you can create a NAND element, and we are able to create a NAND element, we've done this numerically, we need to verify this experimentally. Once you have the NAND, then you have the universal gate that can do anything a computer can do, but of course you can do it acoustically. Now, we'll never be as fast as a computer manipulating electrons, and that's really not the point of what we're doing. What we're trying to do is take advantage of acoustics and the structural elements of an engineered device, let's say, if you like, a robot. We're trying to use acoustics really to make the structural response of the robot smart and to do computing in basic logic so that it can then offload or unburden the traditional CPU, which is doing many things, vision, making many decisions, is really an overtaxed system in many cases. We'd like to offload some of that burden and do it with the structure itself. And this could be called structural computing. Some people call it morphological computing. And so our big interest under NewFoS now is how do we take advantage of some of the technology we developed in order to enable some type of logic or computing of the structure itself, unburden the CPU, and essentially increase the capability of a structure itself to do basic computing. And I'm super excited about that. That's work that we're going to be doing under NewFoS in the next few years.